Okay, welcome back, ladies and gentlemen. We are on to related rates case 3 of shadows, and this one's a little bit different, although still not hugely complicated. So let's set up the scenario. So this time, this is actually not going to be a lamppost. It's going to be the wall and the ground. And then what we're going to have is, instead of having a lamppost with a light source at the top, we're going to have a light source down right at the ground. So that could be in the form of a spotlight shining on the building, or we've left a lamp on the ground, or there's a lightning bug, a firefly that's like nuclear bright. There's some light that's being given off. And then what we have is, maybe this is a firefly, and what we have is Bhavya. He's here. So here's Bhavya. Bhavya has hair. Bhavya is deathly afraid of fireflies, so she is running away from the firefly towards the house. So Bhavya, she is booking it. She's running at 3 meters per second away from the firefly. Okay, so there's Bhavya. She's running away from the firefly. So what we're going to have is, you can imagine the firefly that is just glowing incredibly luminously is casting a shadow from Bhavya onto the wall. So here is Bhavya's shadow. And what I want to know, so case 3 is going to be how quickly is the height of the shadow changing when Bhavya, I hope I spelled that right, I don't know, is, how about, let's say, when Bhavya is 4 meters from the wall. So when Bhavya is 4 meters from the wall. Now, this firefly, in spite of Bhavya's insane fear of it, is not really interested, and it's just kind of hanging out. So the firefly isn't moving. Firefly is going to be 10 meters from the wall. So there's a scenario. Bhavya is booking it towards the wall at 3 meters per second. Bhavya is 4 meters away from the wall when we're interested in finding out what's going on, and the height of Bhavya's shadow is changing. I want to know what rate of change her shadow is experiencing as she's running towards the wall. So we've got 2 similar triangles. I don't really need to draw them on the triangle here. We'll keep it a little bit cleaner because I'm sure that you guys can predict exactly what's going on. So we have the small one. Here it is here. Well, change the dang color. There it is. How about we actually make some straight lines? Kind of a straight line. So here is the smaller triangle. And we know, we know that, how tall is Bhavya? Let's say, Bhavya, how tall are you? I'm going to say 1.6. Which is probably too short, but nevertheless. So Bhavya is 1.6 meters tall. So I know that this dimension here is 1.6 meters. I'm going to leave this one blank. Bhavya also has perfect posture. Good for you, Bhavya. And then there's the bigger one. So we're going to grab the bigger triangle. It would be this guy here. Oh, actually, I changed color. So this one here, I'm going to just draw it down here. Straight lines again. Yay me. So here's the bigger triangle. Not a straight line, nevertheless. So I'm going to call the height of the shadow, I'm going to call it W, because it's on the wall, W. And we know that the bigger triangle it's got a static base on it here. It's 10 meters because the firefly, it's not going anywhere. The wall was built well. It is a right angle, and they share this angle down in here, this angle. So we know that these are similar triangles. This measurement here is relevant to us because it's down here, and I'm going to assign that a variable of b for Bhavya's distance. So I'm going to call this one b. Now, it wouldn't take us, all that long to figure out that in the snapshot, we know that this measurement is actually 6 meters. But I can't substitute 6 in right here in spite of the fact that it seems appealing to do so, because we always have to think, if this problem progressed, is that measurement consistent throughout? Well, throughout the entire problem, Bhavya is 1.6 meters tall. Throughout the entire problem, the firefly is 10 meters away from the wall. But the 6 would not be static, because if we let the problem progress for another second, Bhavya would only be 1 meter from the wall, so this B value would be 9. So because this is a dynamic changing value, we need to actually have a variable for it. So there are my two similar triangles, and I'm going to set up my ratios here. Again, we could go intra or inter triangle. Now I'm gonna, it's interesting, and both methods will work, but one method going forward from here is a fair amount easier, not a fair amount, it's less work if we set this up appropriately. So I'm going to show two different ways that I could set this ratio up. I could say that we're going to have, well, there's more than two ways. There's lots of ways, but I'm going to show you two different variants. So imagine we said, well, 1.6 is related to W in the same way that B is related to 10. Okay, so there's one variant. Or we could say, oh, hey, how about instead W is related to 1.6 in the same way that 10 is related to B. And you say to yourself, well, that's not really all that different. And you're right, it's not really all that different, but it's interesting how the work plays out differently. So I'm going to work both of these solutions through because I think it's important that you can actually see what's going on here. So again, let's think about some of our givens and our wants. I sometimes leave that out because when I'm doing it on my own, I wouldn't bother. But okay, so given, in this case, the way we have this given, we know that dB by dt, that's the rate of change of this, is 3 meters per second. Now, is this going to be positive 3 or negative 3? Pause the video for a second and think to yourself. I'd like you to commit one way or the other. Try and persuade yourself it's going to be positive or negative. Pause it, think about it, come back. Okay, what is it? Well, it's got to be positive. And why it's positive, hopefully you know why it's positive, but I'm going to explain. This B value represents this length right here, right? And if Bobby is running this direction, B is increasing, right? So because B is increasing, the dB by dt must be positive. So I'm not going to write it in positive, but it certainly is not negative. If Bobby was running toward the firefly, which she's not going to do because she's deathly afraid of them, but nevertheless, if she was, then dB by dt would be negative. Okay, so you might look here and think, okay, I don't see why it really is relevant which way I have this written. Because if I cross multiply, it'd be the same, which is true, but I would resist the cross multiplication here because if I cross multiplied, I'd have BW and 16. The BW, if I differentiated it, then I'd have to use product rule. These are, separated nicely, so I don't have to use product rule. So imagine I'm going to do these two kind of side by side. So we're going to have 1.6 W to the negative 1 is equal to 1/10 B. And over here, we're going to have 1 over 1.6 W is equal to 10 B to the negative 1. And you think, okay, well, I mean, it's not really all that different. And it's not. But here we go. I'm going to differentiate. So I'd have negative 1.6 W to the negative 2 dW by dt is equal to 1/10 dB by dt. Okay, fair enough. That's not all that big an issue. I'm going to differentiate this one. So we're going to have 1 over 1.6 dW by dt is equal to negative 10 b squared dB by dt. And you look and you think, okay, well, I got a dW by dt, a dW by dt, and dB by dt on both sides, right? So dW, dW, dB, dB. This one has b's as a variable, and this one has w's as a variable. So it doesn't seem like there's a really big difference. But if we were to follow this one, so the left one, through, what would we get? Well, the W is not explicit in the problem. The W is an unknown. Whereas the B, while not explicit, it doesn't take us long that if we know that this is 4 to know that the snapshot value for B is 6. So I know what dB by dt is. I know, or I found very quickly what B was. So solving for dW by dt is not a challenge. Over here, well, I know dB by dt and I want dW by dt, but I don't explicitly know what W is. It's not that big a deal. We could take this relationship right here, right? And we know that for the snapshot, the B is 6, and then we could rearrange and solve for W, and we could use that as our snapshot value. So certainly all is not lost, and we could progress down here, but it is more challenging, right? So more challenging. And I would encourage you to, I'm going to flesh this solution out just to keep this video as short as I can. I would encourage you that after I've done and demonstrated this, that you continue this problem and make sure that we get the same value. And if we don't, well, then there's going to be an issue there. So I'm going to continue down on this problem. dw by dt is what I'm after. The b value, we said, using a little bit of deductive reasoning, the b value, the snapshot here, is going to be 6. So we're going to have 1 over 1.6 dw by dt is equal to negative 10 times 6 squared. And dB by dt, that's Bavier's speed. We know that was a given. That was 3 meters per second. So I'm going to come back here and say times 3. And so dw by dt, I'm going to multiply both sides by 1.6. Multiply by 1.6, so multiply by 1.6. And we're going to then drop that all into our calculator and see what the value is. So what do we have? We have so negative 10 times, oh, hang on, that's to the, dang it, that's to the negative 2. Come back here. In class, someone would have pointed that out to me. I don't have all the helpers out there that like to make fun of me and get it right. So that's negative to the negative 2. That's important. So back here, so 10 times 6 to the exponent negative 2 times 3 times 1.6. Okay, and so we do that, and we're going to get negative 1.3. So it is negative 1.3 repeated, and that would be, of course, meters per second. So what we have said, and then does that make sense that her shadow is getting shorter? Of course it does, because if she's standing right in front, her shadow would be enormous, and as she gets closer to the wall, it's shorter. So we would say that, therefore, the height of the shadow is decreasing at 1.3 repeated meters per second. And there it is. So there is the third case. So those are the 3 distinct cases. The first 2 are similar, and in fact, you could decide that you will really like one method better than the other, and then just do some some kind of cognition and figure out one case from the other, and then the third case is a little bit different. And we're eligible to ask all of those questions. So I'm going to create some more questions that I will post to Google Classroom in addition to this video. I hope everyone is well. I'm going to try and schedule, I would love to have a Google Meetup with everybody just to kind of see your smiling faces. Like legit, I would love to hear you and see you. So I'll try and set that up maybe later in the week. Stay tuned. Okay, nice seeing you guys. Bye.